Okay, super. So this means we can start. So welcome back to this lecture of models of quantum computation. Yeah, so let's just get started with this week. So we are continuing with the stabilizer formalism. So this is an outline for today and tomorrow. So this is lecture 7 and lecture 8 tomorrow. So we will be talking about the Gottesman-Knill theorem today, and tomorrow we talk a little bit about quantum error correction and certain non-Clifford gates and how you do them with stabilizer quantum codes. So this latter point will provide us with a practical justification for the first scheme of quantum computation that we are going to discuss, quantum computation with magic states. Okay, I mean, we're not so interested in practicalities here in this course, but it's interesting nonetheless. Okay, and so I will do this from now on. I think I should have done it earlier to also tell you when I'm giving these lectures what they are based on and what good reading would be for you. And so for today, for this quantum error correction part, it will be the Nielsen and Chuang, our textbook, and then the PhD thesis of Daniel Gottesman, and then a paper that he wrote on the stabilizer formalism. Okay, so let's recap a little bit what we learned about the stabilizer formalism last time. So we learned what the stabilizer state is, namely a state that is the joint eigenstate of a bunch of commuting Pauli operators with a bunch of extra conditions. So the identity cannot be in the stabilizer group. Maybe you remember why this is so. Okay, and just to have an example, we could, for example, look at the Bell state, just one of the 4 Bell states here, with the 2 spins aligned and a positive relative phase between them. And then you could check that this state is the eigenstate of the Pauli operator sigma z tensor sigma z, and also eigenstate with eigenvalue 1 of this operator sigma x tensor sigma x. Yeah. So these 2 Pauli operators are in the stabilizer, and in fact they generate the stabilizer. So generate means that every element in the stabilizer is a product of these. So there's 2 more elements in the stabilizer, the identity and the Pauli operator minus sigma y times sigma y, which is just the product of these 2. Okay, so that's a stabilizer formalism to the extent we had it in the first example. Clifford unitaries. So Clifford unitaries go well with stabilizer states. And here again is the definition. So you have some Clifford gate, and what it does is it takes any Pauli operator and maps it into a Pauli operator under conjugation. I mean, for general unitaries, this wouldn't be the case. And so it's a restriction, and that restriction defines Clifford gates. And that property we will use in what we discussed today. The immediate consequence is that stabilizer states are mapped onto stabilizer states by the Clifford gates. And so Clifford gates, stabilizer states fit together well. So final ingredient, the measurement of Pauli observables. So we have discussed how to describe a measurement earlier. So measurement in a certain basis or of a certain observable is associated with projectors. You remember Dirac projection postulate and so on and so forth. And here are the projectors that would be relevant for the measurement of a Pauli observable. Pauli observable P here has eigenvalues +1, -1. And so the projectors, as they are supposed to be, have eigenvalues 0 and 1. If you apply these measurements, it turns out that here too, stabilizer states are converted into stabilizer states. Yeah, and what the resulting stabilizer is, this is something we will talk about today. But the upshot so far is that stabilizer states, Clifford unitaries, and Pauli measurements form a closed subtheory of quantum mechanics. If you start with the stabilizer state and then only apply Pauli measurements and Clifford unitaries, and then more Pauli measurements, more Clifford unitaries, you do not get out of the set of stabilizer states. And so in that sense, this is a subtheory of quantum mechanics, and we want to know what's in it. Is this interesting quantum mechanics, uninteresting quantum mechanics, Well, we'll see. We'll see this today and tomorrow. Okay, so here's maybe the negative news, so to speak, and that's the Gottesman-Knill theorem. So it says that the evolution we just discussed, stabilizer states evolving under Pauli measurement and Clifford unitaries, this can be efficiently tracked. So this evolution is efficiently classically simulable, and we'll talk about today how that proceeds. And so this means that the stabilizer fragment of quantum theory does not offer quantum speedup. So if you want to do quantum computation, we need to do more than this. So I mean, at this point, maybe stabilizer formalism looks pretty useless, but that's not at all the case. So the theory of quantum error correction largely builds on the stabilizer formalism. I mean, if you didn't have that formalism, proofs of fault tolerance would be pretty incomprehensible. So it is an important and powerful tool. And we'll see about that part tomorrow. And so now that was the kind of the phenomenological point, and now there is a technical point here, a point about technique. And so the stabilizer formalism is all about mod 2 linear algebra on binary valued matrices, which are furthermore small. Yeah? So it's very simple operations that it all boils down to, and this mapping we want to do today. So let's get started. So this is the result that we want to prove today, the Gottesman-Knill theorem. And yeah, now we want to get started with that. So there's two tasks. So given a stabilizer state and a Clifford unitary, what is the stabilizer that corresponds to the transformed state u psi? Yeah, so the task is to construct a representation of that stabilizer. It's the task number one, yeah? Update under Clifford unitaries. The second task concerns the update of a stabilizer state under Pauli measurement. So again, we want to know, there's two things now. There is the probability distribution of measurement outcomes. Yeah? So we can measure up or down for any Pauli measurement, two eigenvalues. Yeah, what are the probabilities for getting these two outcomes? That's one part, the measurement outcome, but then there's a Dirac projection postulate. You also want to know the state after you've done that measurement. Okay, so these are the two tasks that we want to deal with. And our observation here is, well, first, we need an efficient presentation of the stabilizer group. A stabilizer group has exponentially many elements. It's too many for us to write down. And yeah, we want an efficient presentation of it. And an efficient presentation, maybe I say this before I go into all the linear algebra stuff, an efficient presentation will have to do with just listing the generators of the group. So this is polynomially many. In fact, it is as many generators as you have qubits. Yeah, so, and the generators, of course, fully specify the group. Okay, so this will be the first step of simplification. Okay, Pauli operators and bit strings. So this is really how we get started. Okay. Okay, so there's a lot of text here on this slide. Maybe let's begin in the middle. Yeah? Let's begin with this line. So we have a Pauli operator. So this is denoted P of A. P is for Pauli, but what is the A? The A is a vector of a certain length. Yeah? So a 2n component binary vector. And how do you use this vector? You use it like such. Yeah? So your Pauli operator will be a product of local x's and local z's. And so what this binary vector is used for is you're switching on and off these powers. Yeah? Say x1 to the power 0 is just the identity, and x1 to the power 1 is just this x1. Yeah? So with all these powers here, with these binary valued things, you're switching on these x and z contributions to your overall Pauli operator. Yeah? So this is what the A is. Then you have phase factors here. So let's talk about them too. But that's the most important thing. So we have a we have a vector A that has two n components with bit-valued entries, and that determines a Pauli operator up to phases. Yeah? So that's the most important thing that this slide is supposed to convey. And so this is how our mod 2 linear matrices and operations come in. Yeah, so that's the most important thing. But we do have to clean up these phases here a little bit, so we have to talk about them too. We'll talk quite a bit about phases and sign factors as we go along. But the most important thing is this binary vector up there, which appears here specifying the Pauli operator. So now let's talk about these phases. We want our observables measurable. So for qubits, we want them Hermitian. Later we will talk about Q-trits and 5-level systems and so on and so forth. Then we have to give up hermeticity, but for now we can have it. Later we will find other reasons. But yeah, we want hermeticity for now. And so that's why we have this I here. So let me just quickly tell you how this comes about. So suppose there's just one qubit 1. And so suppose the vector A is such that you have the X part and you have the Z part. When that happens, X and Z multiply to either plus IY or minus IY. I just, let me see. Well, you can figure that out, which one of the two it is. But for sure you will not be Hermitian because you have the I there. And that I you need to cancel. Yeah? So that's why you would have an additional factor of I. And you see, only if the X bit and the Z bit are set, this inner product equals 1. Yeah? To compensate for the I that you get from the operator multiplication. So that is why you have the I factor here. Yeah, so this is why you have it there. So just to make these matrices Hermitian, yeah, so that you can measure them. In view of what's going to come later, if you don't want to rely on hermeticity, what you would say is you put this factor here because you want the eigenvalue spectrum to be plus minus 1, what it is supposed to be, not plus minus I. Yeah? So that's another way of reasoning why you want this factor here, and that way of reasoning would then carry over to other dimensions. Okay, so that's taking care of hermeticity such we can measure these beasts. And so now we have the freedom of a sign. Yeah? So we can add a -1 that will not fiddle with hermeticity, it would just exchange the eigenvalues, but the set of eigenvalues remains the same. So that's all fine. So we can have it or not have it, and we can specify this with another bit that is a function, if we want it to be, of this vector A. Okay, so this is a freedom that we have, but we will not use it. So that's coming up on one of the next slide. So this is a convention, or a gauge if you like. And so we can set that whatever we want. It will not affect our reasoning much, which is why we will set it to 0. But that's a convention. Good. Okay, so the upshot is we have a bunch of Pauli operators, or any Pauli operator, and we can specify it up to a sign at least by this binary vector A. And that will become very important for today. Okay, so yeah, now comes this gauge thing. So we choose this function eta to be identically vanishing. So just to get rid of it, I don't have to write it all the time. Yeah, okay, and so now these bit strings there, so they are 2n component binary vectors, and so they form a group under addition. And so now we may ask, okay, so the Pauli operators form their own group. What do they have to do with that group Z2 to the 2n? Okay, so let's talk about that a little bit. Okay, so remember this was our expression on the last slide, how we relate a Pauli operator to this bit string. And recall that we have this factor there for hermeticity. And now we are asking, how does this Pauli operator for the vector A plus the vector B, I should say, so these are binary valued, so these vectors add modulo 2. Sometimes I forget to write this down. But addition among these vectors is always mod 2. Okay, so you wonder, is this the product of the two? If this was the case, then these Pauli operators would form a representation of that group, yeah? Z2 to the 2n. Okay, but that's not actually the case. If you work it out, you have this extra factor sitting there that depends on these vectors A and B. And it turns out that maybe we choose the wrong function eta. So you wonder, can we get rid of this factor maybe by a better definition of eta? And it turns out you cannot get rid of it. And so the upshot of this is that the Pauli operators do not form a representation of this group, but they form what is called a projective representation. It's furthermore, I see nodding here in the room, it's a non-trivial projective representation, and some of you know what projective representations are classified by. And yeah, group cohomology will appear in this lecture too, once in a while. Okay, good. So it's a projective representation. It's non-trivial because you can't get rid of this factor here by redefining phases in the Pauli operators by changing eta. Yeah, okay, so now I have to sit down and calculate something. So we want to know what happens under commutation. So in our formalism with these binary vectors A and B, we want to have a way of deciding whether Pauli operators commute or anti-commute. Yeah? So we discussed, I think at the very beginning of this class, that there's only these two choices for Pauli operators. They either commute or anti-commute. And so we want to know for two given Pauli operators, which of the two is the case. Good. Okay, so let's calculate that briefly. Okay, so what is this here? So we have the Pauli operator A plus B, but addition is commutative, so this is equal to that. Okay, and so I can now use this expression up here with A and B interchanged. Good, so let's figure that out. So this is e to the power, A becomes B, so we have AZ BX minus AXBZ and times P of B times P of A. Okay, and so if we now compare these two exponents, we find that the new exponent here is just minus the old exponent. Okay, so just by direct comparison. So this part reappears here, and this negative part reappears as positive part here. So indeed, this whole thing is minus of what you have there. So now, therefore, it follows that PB, P of A is, now we have this exponent squared, so we have minus 1 to the power AX BZ minus AZ BX P of A times P of B. Okay? So so now we see directly whether these two Pauli operators commute or anti-commute hinges on this type of inner product. Yeah? And so we make this a definition. This type of, sorry, I shouldn't call it inner product, this type of product. Yeah, so we give this thing a name. Yeah, okay. So commutation is an important thing that we want to keep track of, and we find that there is an efficient way of calculating that, whether the two Pauli operators commute or anti-commute, just from these vectors A and B, the corresponding vectors A and B. Okay, and so yeah, we define this object. We'll find lots of uses for it. And this also gives you an explanation why you can't get rid of these phases, because if you could get rid of them, you could never realize a factor of -1 here in this commutation. Okay, anybody still writing, or are we done? Done writing? Good. Okay, so let's see. Yeah, so this is now just a little bit of just introducing more notation. So this is basically what we had on the previous slide. And we can write this in a bit of a different way. So we realize that this is a bilinear expression in our vectors A and B, and so we can write it using a quadratic form. And this quadratic form has a name. It's called the symplectic form, and it looks like this. Yeah? So it has 0 blocks on the diagonal. So I should say, what's the size of this thing? So if we have n qubits, then these vectors have 2n components. And so this is a 2n by 2n matrix. And we are coupling x part with z part. And so on the diagonals, the blocks are 0 because they would couple xx, z and z. Doesn't happen here. And here you see the off-diagonal blocks, they couple the x and z parts exactly as you see it here. Good. Maybe to make this clear, I should write the transpose. So this is vector inner product. Okay, good. So that's called the symplectic form. And yeah, so this is also going to be important. Maybe to give you okay, I'm getting ahead of myself. I will come back to these symplectic things later.
Should there be a minus sign somewhere in the S?
Oh yeah, in principle, yes, but it's modulo 2. So you can, you choose your sign. Okay, let's add it if you prefer, but it is modulo 2, so here it doesn't matter. Later, when we move from qubits to systems with more levels, then the signs will matter, but not for now. Good, okay, so then let's move on. Okay, so this is our definition of Pauli operators in terms of bit strings. So now we want to stack certain Pauli operators together to form a stabilizer. And this is the stabilizer generator matrix. It's usually written as this curly G here. And this is how it is, what it looks like. So let's, so we have n rows 2, yeah? So we have 2 blocks here. We call these blocks curly gx and curly gz. So they are of size n times n rows, n columns. And so the left block is for the x part of the stabilizer. So it has these vectors ax in it, and this right half here is g curly gz. That's for the z part of the stabilizer. As rows of this matrix, you have these vectors A that define your Pauli operators, or that define certain Pauli operators. So they decompose into an x part and a z part. And which Pauli operators do they refer to? They refer to the Pauli operators that generate a stabilizer. So they have to be pairwise commuting. That's what you have in a stabilizer. And otherwise, they are just Pauli operators, and they generate a group. So yeah, so so the stabilizer generator matrix is a matrix of size n, yeah, n rows times 2n columns with binary entries only. So this is not a whole lot of information. It's just a bunch of bits, and they define this. I mean, modulo science, there's something we still have to talk about, but by and large, these 2n squared bits define a quantum state, stabilizer state. Actually, it's not even 2n squared because of the commutativity constraints. So it's a little less, about half as much. So, so that was a stabilizer generator matrix. But now, what if it's not the Pauli operator P of A that's in the stabilizer, but rather minus P of A is in the stabilizer? Both can happen. And so we need to have a way of keeping track of these signs. And so you don't only need the stabilizer generator matrix, but you need a corresponding vector of bits that tells you whether plus or minus P of A corresponding to all of these rows here is in the stabilizer. So you need that thing too for the signs. But still, this is order n squared bits, so this is an efficient description of quantum states whenever it applies. It doesn't apply to all that much. It's a finite set of states, but yeah, when it applies, it's a very efficient description. Good. So that is the stabilizer generator matrix. And here we have made the transition now from Pauli operators to vectors of bits. So, and as you will see as we go along, we now do linear algebra transformation. So we will multiply the stabilizer generator matrix with certain matrices from the left and right. So it's all linear algebra on these rather compact matrices. Good. Okay, so this is what a stabilizer generator matrix is. Okay, I think, let me see what's coming up. Example. Okay, so just the simplest non-trivial example. We are looking at a Bell state, a particular one, also known as the spin singlet. So we have spins here that are oriented in opposite directions in all bases, so specifically in the eigenbasis of Z. Okay, and so this is a stabilizer state. And so we can use our old notation for the stabilizer group as generated by a bunch of Pauli operators. We can easily verify that minus x tensor x is in the stabilizer. Just apply it. And so you see x tensor x would exchange the two terms. Because we have the relative phase here, it would take the state to minus itself, and you have the minus here to compensate for that. So that this is indeed a stabilizer taking the state back to itself. Similar argument holds for this. So they are both in the stabilizer, and in fact they generate it. So this is the picture we already developed last time. Now we are using this linear algebra description instead in terms of the stabilizer generator matrix. So the left half of the generator matrix is always for the x part. It's just the convention. The right half for the z part. So, so this operator corresponds to the first line of the stabilizer generator matrix. x1 tensor xz, x1 tensor x2, no z part, and the minus sign is encoded in here. So the minus sign is -1 to that thing. So second generator in the of the stabilizer, nothing in x times z1 times z2. Again, minus sign is encoded here. Anna, where is the third minus sign? So that was the states. And so now we move on. We remember we had two tasks. One was to figure out what the update is on the Pauli measurements. That's the second thing. And the other thing is the update on the Clifford unitaries. So I'll be more formal about that in a moment. But for now, we just look at an example. So that first example basically tells us everything that comes up. So it's a reminder for us what we have to take care of. Okay, so we know what the Hadamard does. It exchanges the eigenbases of x and z. We remember that, I think. So x, when conjugated on the Hadamard, becomes Pauli z. Same for the z. Conjugated on the Hadamard becomes the x. And so now we also want to look at what happens if the Pauli operator y, sigma y, is conjugated under the Hadamard gate. And we wanna figure this out using the two relations that we have already found. And so to facilitate that, we realize that the sigma y is minus I times zx. And so now what we do with this is, okay, so we are making an insertion of the identity h dagger h. H is unitary, so h dagger h is the identity. So, okay, so now we can put the brackets in a way that suits us. Okay, and here you see now we can use what we had above. Yeah? So we have the z conjugated, which we know is x, and the x conjugated, which we know is z. So this gives minus I x z. So we see, oh, we pretty much get what we started from, but in the opposite order. So we exchange the order. So this gives us a minus sign. X and z anti-commute. So this is plus I z x. Okay, and so now we do the identification backwards that we used at the beginning. So this is minus y. Yeah? So y goes into minus y. Okay, so to summarize, what we have to do is to take care of what these Pauli operators do, or rather the bit strings describing these Pauli operators, but also we have to take care of these signs. Yeah? So we cannot just let them fall off the table. We have to take care of them too. So this is what we'll have to do. Two things. Namely, what Pauli operators conjugate into, and we want to describe this in terms of a binary vectors, of these binary vectors that we introduced, and then we want to take care of those signs. So this is our job now when describing the update of stabilizers under Clifford unitaries. So now here's the same thing, a little more formal, but I mean, you have seen it in the example. So we are dealing with task 1 now, update under unitaries. And so by definition, for any element in the Clifford group, a Pauli operator is updated by conjugation under this gate. Okay? And so now we look at this expression. So now we're looking at Pauli operators that are labeled by these bit strings, or by these bit-valued vectors, and see what happens to them. So two things. So this label, this vector label of the Pauli operator will obviously change, and that change will depend on what that group element was in the Clifford group. And also we will have these phases. So that's something that we just saw in the Hadamard example. So these are the two things that we want to figure out. I mean, all these objects here, mapping A into G of A, can this be efficiently computed? What kind of map is this at all? These phase functions, this is what they are called, phase functions. Are they efficiently computed as a function of what G is and what A is? Yeah, so these things are the subject of our next discussion, the update under Clifford unitaries. And so with the phase function we deal a little bit later. First thing is we want to know what kind of map these are. Yeah? So they are mediated by group elements. How do they act on these binary vectors? Okay, so that's that's the thing we deal with first. So the conclusion is already on the slide. It will be a linear map, and now we want to see why this is. Okay, so what did I have? Okay, so I need to figure out these steps. Okay, all right. So let's transform this a bit. So this sign again looks maybe a little weird, but it's just proportionality, and so I don't want to be bothered with all these sign factors in front. That's why I'm writing this. Yeah, and so this is equal to. So we know that up to sign, this thing here, this Pauli operator is P of A times P of B. Up to sign. Okay, phase. So, okay, so let's use this. So this is U of G, I mean, what is this notation even? U subscript G. So G is here an element in the abstract Clifford group, and U is a unitary representation of that abstract group element acting on our Hilbert space. Yeah? Good. So, okay then, so now this thing in the middle is proportional to P of A times P of B, and then we have U dagger. Okay, and so now we play the same trick again that we just used. We insert, excuse me, we insert an identity. Oh God, this is a little bit messy. P of A, UG dagger, UG P of B, UG dagger. Okay, we can put brackets as we please. This is associative, so this is furthermore proportional to. Now, so remember that formula here. So this formula we are using now, except that we don't care about these phases. Okay, so this is P proportional to P of GA, coming from the first bracket, P of GB coming from the second bracket, which is proportional again to P of GA plus GB. Okay, and so now we compare what we have here versus there. Yeah, so it's the same vector under the Pauli. I mean, in the argument of the Pauli. So the conclusion is that G of A plus B, so the arguments must be the same, otherwise it cannot be the same Pauli up to scalar factor. So the conclusion is that G of A plus B equals G of A plus G of B. Yeah? And so this means we have a linear map here, modulo 2. Yeah? So all addition here is modulo 2. Yeah, so we have, so this property here is telling us that we are dealing with a linear map. So that is a very significant simplification. So it's not an arbitrary map, it is a linear map. But let me just finish this. So it is a linear map, but then there's another property. And the property is that all these Clifford group elements, they preserve this symplectic form. Yeah, remember this information about the commutation, or we might just call it the commutator if we like. This contains the information of whether two Pauli operators P of A and P of B commute or anti-commute. And that needs to be preserved under this linear map G here. And the reason is G describes the application of a unitary transformation, namely U of G. And when we are conjugating under a unitary, we preserve the commutation or anti-commutation. Yeah. So if you have two Pauli operators, you conjugate them under any unitary, doesn't need to be Clifford, then the commutation will be preserved. If they anti-commuted before the transformation, they will anti-commute after. If they commuted before the transformation, they will commute after. So the commutation relation is preserved. This must hold in particular for the Clifford gates, and then it has bearing on this quadratic form. So this quadratic form is preserved because it represents commutation. Okay, and linear transformations with this property, they are called symplectic transformations. So this is the standing terminology in linear algebra. Okay, so just so that we know what these are. On the next couple of slides, and that's probably after the break, we will look at a few examples of that. So this was the last thing we did before the break. We realized that this map here, G, which is changing these Pauli labels. Yeah, it's changing these Pauli labels. We had label A before the transformation. We have label G of A after the transformation. What is this transformation G? And it's a linear map. So that's what we figured out. Preserves commutation. So these are its structural properties. They make it a symplectic transformation. Okay, now let's look at that in examples. Yeah, so it's something that we've known for a long time. Hadamard takes an X into a Z and vice versa. So now we can describe this linear map by a matrix. We call this matrix M subscript H because it refers to the Hadamard, and I have M for, what do I have it for? For modular representation, but never mind. You can also read it as matrix. Anyway, there is a matrix associated with this application of the linear map. So what would it look like? It would look like this. Yeah? So it takes, so this is what it would look like. And the question is why? Okay, so we can check it out. So if we apply this matrix to the vector 0, 1. So the vector 0, 1 x part comes first. So this would correspond to a Pauli x. Yeah? We multiply it, gives us a vector 0, 1. So this corresponds to a Pauli z, exactly as we expected. And the other way around works just the same. So we apply it to a vector 0, 1. So this corresponds to a z. And when we multiply it out, just matrix multiplication, we get the vector like so, and that corresponds to an x. Good, checks out too. Then there's the matter of the phase function. Yeah, we remember we need that, but we'll talk about that later. So for now, we only look at these binary vector valued Pauli labels. So that is the corresponding matrix. So what this Hadamard gate does on stabilizer states and Pauli observables is all encoded in that matrix. Yeah? So we are representing a quantum gate by a matrix. Okay, so so right now there's no gain in size. This is a two-dimensional Hilbert space, just one qubit. Yeah, so the normal unitary matrix would be a 2x2 matrix. Here you have a 2x2 matrix of binary entries, and not smaller, except now it's only a matrix over bits, not reals. But when you go to n qubits, this matrix will only be linear in size. It will be 2n times 2n rather than of size 2 to the n by 2 to the n. Yeah? So you see the efficiency of description coming up when n gets larger. So that was the Hadamard gate. So now we do a bunch of other gates. The reason we do this, a few gates now, namely 3 of them, is that without proof, the gates that we do here generate the Clifford group. Yeah? So remember, we had a universal set that generated SU2 to the n. Again, we have the same concept here for the Clifford group. It is generated by a small set of gates. And so that's the Hadamard. That is a rotation about the z-axis with rotation angle pi over 2. And then the CNOT gate. These 3 gates generate the Clifford group. Okay, so let's look at that. So what does this S gate do? It takes x to y, and it takes z to z, yeah? So z commutes with itself, so z remains unchanged, but x goes into y. Okay, we can encode these relations in a binary valued matrix. So first, what happens to an x? X is represented by vector 0, 1. So this is supposed to give us 1, 1, which represents the y. And therefore, you have this first column here. And the second column is just for what happens to the z. Yeah, and the z just remains itself. So this is the corresponding binary valued matrix for that gate. Okay, final gate here from our generating set. Yeah, so the CNOT. So we have seen earlier, I think we did this calculation in an earlier class. So for the control qubit, if it's conjugated by the CNOT, it becomes what it was, tensor x on the other qubit. So it becomes a non-local observable. On the target, the x remains just what it was, commutes with the gate. The z on the control also commutes with the gate, so it's conjugated into itself. And finally, the z on the target again becomes a correlated observable z on the control times z on the target. Okay, and so these 4 relations define our binary value matrix that corresponds to the CNOT gate. Okay, so first relation, x on the control. Control bit comes first. So it remains of x type, but becomes correlated. So that's why in the first column, you have a 1 here and a 1 here for x on both of the qubits. There's no z contribution here. The x on the target just stays itself, so that's what you see here. No x on the control, no z portions either. Okay, and then for the z, you have a similar looking contribution to that matrix. So the control, which is the first qubit here, remains itself. No z on the target, no x contributions either. And finally, the target z becomes correlated. So you have a contribution for the target, contribution for the control, but no x part. So this is how this matrix come about. Okay, so now we've seen it for a bunch of Clifford gates, and it turns out these 3 gates, they generate the Clifford group. Therefore, for any Clifford circuit, we can update the stabilizer generator matrix under Clifford unitaries, and this is efficient. It's just by multiplication of these Pauli string operators by these vectors with matrices. Final comment for the slide. If you go to the stabilizer generator matrix, I don't know how far, oh yeah, here it is. So what we've just discussed was multiplication on column vectors A. Yeah, so, but remember here in the stabilizer generator matrix, those vectors A are row vectors. Yeah, and if I multiply the column vector A with a matrix M from the left, from your perspective, from the left, then the corresponding row vector, which I get by the transpose, I will update by multiplying from the right with the transpose matrix. Yeah? So point is, here we are dealing with row vectors, so the update of the stabilizer generator matrix is by multiplication of matrices from the right. Yeah, so this is how we apply gates to the stabilizer generator matrix by multiplication from the right, and this has to do with transposition because those vectors are row vectors here, not column vectors. Good, just wanted to say that. And I pause for questions.
Do the indices mean at the C0, S, and H, the indices for the union?
These, what do they mean? Okay, so up here I spoke about the C0. But if we have n qubits, I mean, they can act on any 2 out of n. Yeah, and I call these I and j. Yeah, and then I have another label k for these S gates. They can also act on any of these qubits, and H the same. Good. Okay. So if you want, I'm not commenting on the left half of the room. So this is a large fraction of update on the Clifford unitaries, but we have to talk about the signs. So there's a relation we had earlier. So with our conventions for the Pauli operator P of A, I mean we are fixing a sign, and it can happen that the Pauli observable with the opposite sign is in the stabilizer, so we have to have this freedom here to fix the sign. So that's what we have this other vector for. And now the question is, how is this vector updated under a Clifford gate? I mean, this thing is updated, so seems reasonable that this vector is updated as well. Okay, and that's what we're gonna look at now. And here is how these phase functions come in. Okay, so let's look at our stabilizer generator matrix, and in particular at the nth row of it. So we are looking at a row vector at row number L, and this represents one stabilizer Pauli operator for us. And it has the Pauli operator specified by the nth row of the generator matrix, and then it has this sign coming from this vector V. Okay, and so now we do the update on the Clifford gate, which is by conjugation. Basically, we have written down what happens. So this prefactor that we already had is completely unaffected. It commutes with the action of the unitary. And so now the unitary directly acts on this Pauli part by conjugation, and we know what that is, what that does. Namely, it produces another factor -1 to the power of the phase function, and it changes the Pauli label here. Okay, and so that we have now discussed at length, and these functions we still have to discuss what they look like, but we can now identify the transformation behavior. So what happens is that this sign represented by this binary value VL is updated according to this formula. So basically we take what we had and update it with the phase function evaluated for the Clifford gate G that we are doing and the binary vector of the Pauli observable that we are transforming. Yeah, the phase function has 2 arguments, a group element and then an element from this vector space. So that's that update. Yeah, we're making some progress here. We're not done yet with the Gottesman-Knill theorem. Okay, so what we have so far seen is that the update on the Clifford gates is efficient if we can efficiently compute that phase function here. And that we still need to show. I mean, we have to compute it potentially for all Clifford gates and all of these binary vectors. Okay, and it turns out rather than doing it in general, it's better to do it for examples, or simpler to do it for examples, namely for the generating set, which is the Hadamard, the S gate, and the C0. So we observe that if you just have a single qubit, all 3 X, Y, and Z are in this set P of A with the proper signs, and that observation will help us here. So for the Hadamard gate, I mean, we've done this now multiple times. The x goes into z, z goes into x, y goes into minus y. So we have a sign only if the x bit and the z bit of this vector A are set. That is, the phase function is, yeah, so the phase function is just this, yeah, product of ax times az. Yeah, okay, good. Okay, and what is important about this, that it is a quadratic expression. So that's all. Same thing for the S gate. So x goes into y, y goes into minus x, z goes into z. Okay, so we have, again, a minus sign only for the y, and so the phase function is the same in what we had. It has to be 1 for the vector 1, 1, and 0 otherwise. So it's again the same quadratic expression. Okay, so final thing for the C naught is a little bit more complicated, but you can work it out at home if you want to. So you think, oh, nothing's going to happen here. The x part remains itself and the z part remains itself. But actually, it's not so straightforward. So you would think that maybe the phase function is 0 here, but it's not. And I want to just show you where the matter is. Okay, so consider this Pauli operator. X on the control, tensor Z on the target. So the X conjugates into X tensor X, and the Z conjugates into Z tensor Z. So that's what you're left with after the conjugation. And so if you multiply it out, then this gives you minus Y tensor Y. But then if you look up our phase conventions, then you will find that plus Y tensor Y is in the set P of A. So you get an additional minus sign in this particular instance. But this means that the phase function cannot be identically vanishing. It must be something else. And you can work it out. I don't want to do it here, but again, it is a quadratic expression. It's quadratic, so it's efficiently computable for all the gates we discussed. And so now you have everything for the update under these 3 gates, Hadamard, S, and C naught. And so now you can simulate every Clifford circuit. Namely, you can, if you want, you can simulate it step by step. A tiny bit more formally, it's maybe unnecessary ambition, but at any rate, I want to show you how the phase function behaves under composition. Yeah, so basically the statement that you can, what I just said, that you can simulate step after step after step. Yeah, I wanna make this a little bit more formal and show you how to compute the phase function for a Clifford circuit that is a sequence of gates. Okay, so here let's just consider 2. So we have a product of elementary gates that we have already dealt with, and we want to know how a Pauli observable P of A is updated under this product. Okay, so then there's 2 ways of working this out. So it is P of HGA times minus 1 to the phase function HG with group label HG of A. Okay, so this is one way to figure out what's going on. And then there's another way by just kind of playing with associativity again. Yeah, so we're just putting our brackets differently, like so. Okay, so now what is this? So this is now a step-like evaluation. So this is H of, so that remains P of GA times minus 1 phase function phi G of A. Okay, H dagger, and this is phase factor can be taken out. Now I have the conjugation by H applied to this thing. And so that is So we get another factor of phase function. So this is now phi h of GA. And then I get the conjugated Pauli observable, so I get P of H G A, if you like this. Okay, and so now Pauli observable wise, we have this matching that, and therefore this must match that. Okay, and so we have this relation here. So we have the phase function for the composite circuit expressed in terms of phase functions for individual gates. Okay, so this is the formal expression for being able to simulate latest circuit step by step. Okay, so I have put this in here for a reason. So this thing has a name in algebraic topology. This is the so-called co-cycle condition, group co-cycle condition. So this has a relation, again, to group cohomology, and that is, yeah, so this is a topic that will come up later in this course. I just wanted to mention. So now I think we are ready to summarize the unitary part, because, and we need to we have to race through measurement. We need to finish the Gottesman-Knill theorem today. Okay, so for now it's the Clifford update. And so the summary is, well, there's two things to be updated. There is the stabilizer generator matrix, and this will be by right multiplication with a suitable matrix. And well, the other thing to be updated is this vector of signs. And yeah, we have figured out that update too. We further understood that the phase function is a quadratic function in A for any Clifford circuit, and it's efficiently computable. Okay, so no difficulty in classically following Clifford gates on stabilizer states. Good, so we are done with that and move on to measurement. Okay, so this refers to task 2. Remember, a while ago I pointed out these two tasks. One you have just solved, and the other one is remaining. So given a stabilizer state, compute the outcome probabilities of the measurement of a certain Pauli observable, and construct the corresponding post-measurement state. So two things: outcome probabilities, post-measurement states. So we begin with the outcome probabilities. Okay, so there is a bunch of cases here. So let's first look at this lemma. So it says the following, and we'll prove this shortly. So for any stabilizer state and Pauli observable, the expectation value of that Pauli observable with respect to that stabilizer state can only take three values, namely 0, +1, and -1. And here it is when this happens. Here it says when this happens. So +1 is when the Pauli observable is in the stabilizer. -1 if minus that Pauli observable is in the stabilizer, and 0 otherwise. Okay, and so once we have this result, from the expectation value, you get the probabilities. So if the expectation value is 0, then it's 50-50. And if it is +1 or -1, then it is the measurement outcome is certain. Okay, so let's prove the lemma. So case 1 I just omitted, case 2 kind of similar. So we are writing this expectation value here as basically itself with two minuses that cancel one another. But we now observe that -p is in the stabilizer, so it just disappears, and this minus sign outside remains. And so despite the normalization condition, this is 1, we inherit the minus sign, so the expectation value is -1 as claimed. Okay, good. So the main case is case number 3, namely when neither P is in the stabilizer nor -P is in the stabilizer. So now we observe that the stabilizer is maximal. It cannot be extended by an observable that's commuting with the whole thing. Yeah? So suppose we wanted to do this with P, well, stabilizer is maximal, so it cannot commute with everything in the stabilizer. So there is an element in the stabilizer that anti-commutes with P, must be. Okay, and so now we want to look at the consequence of that. Okay, so our expectation value of interest is we're pulling that stabilizer element out. Now we observe the anti-commutation, so this is minus psi s x p psi s. Okay, so that's something I can easily do here. So now I can also add a dagger because x is Hermitian, and then I can put it back in here to the left. So this is minus psi s p psi s. Okay, now I look what I ended up with and what I started with, and I find it's the same up to sign. But if a real number equals minus itself, then it must be 0. Yeah, and so we find that our expectation value is indeed 0 as claimed. Good. So yes, indeed, all that can happen. These three cases. Okay, so here's an outcome, an algorithm for computing this probability distribution. So we have to check commutation with a stabilizer, and as we have learned, we can do this with the stabilizer generator matrix. Yeah, so that's what we do. We check the commutativity condition with the stabilizer generator matrix. I mean of this Pauli observable P of B. So if the commutativity fails, then we are in case 3. And if we are in case 3, the probability of the outcomes is just 50-50, completely random. If that doesn't happen here, so if this thing commutes, B commutes with the entire stabilizer generator matrix, then we still need to move on. So as soon as we are in the second step, there's only 2 possibilities remaining. Either the expectation value is +1 or it is -1. And which of the 2 is the case, we now need to figure out. And so this is by row manipulations. So this is now for the first time that we are operating on rows of the stabilizer. So previously we have operated on columns, yeah, to actually change the stabilizer. Operating on the rows doesn't change the stabilizer, it only changes the basis, but the group remains the same. And so what we do is we do row manipulations in such a way that we find the vector B as a row in that matrix. And yeah, so the corresponding row additions and switches and so on and so forth, we also do on the corresponding vector B, which is always standing on the side. And then we figure out what this value V of B is. If this value of V of B is 1, then we have expectation value -1, and if V of B is 0, then we have expectation value 1. Okay, and once we have the expectation value, then we get the outcome probabilities. Good, so that's the first part of what's happening under a Pauli measurement, so we get the probability of the outcome. So then the update of the stabilizer itself. There's 2 cases. The first case is so that either the Pauli observable that we are measuring or minus of it is in the stabilizer. And so if that happens, we are just producing the deterministic outcome, and the stabilizer itself is unchanged. There's no update in this case. But there is an update if neither the observable that we measure itself or minus itself is in the stabilizer. Yes, case number 2. And in that case, the stabilizer does change. Namely, as we've just observed, if this P of B, either it or minus it is not in the stabilizer, then it cannot commute with all of the stabilizer because the stabilizer is maximal in the case of states. So it must anti-commute with something, and so these elements are removed. These elements are removed from the stabilizer. So what doesn't commute with the observable measured will be removed from the stabilizer. And so we need to figure out how many times this actually happens. So there will be a certain number of rows in the stabilizer generator matrix for which we get commutation with the measured observable, so where this thing holds, and we keep them. And now there is all the remaining rows for which it doesn't hold, for which we have anti-commutation with the observable that we're measuring. Okay, and so they will be removed from the stabilizer. So it seems that we are losing a lot, but that's actually not the case. For we make the following observation. So suppose we have two such rows here. Let's call them A tilde and A tilde prime. Both satisfy this condition. So if we add them up and form the commutator with B, we get 0 again, yeah? 1 plus 1 more 2 is 0. And so this means that we can put the sum back into the stabilizer generator matrix. Let me write that down. Okay, so we have, so this is our generator matrix. We have A1, A2, and so on and so forth. And so now we measure the observable P of B. Okay, let's say A1 and A3. I'll just elaborate here a little bit. So they commute. Okay, so AI, comma, B is 0. And so let's say, so we have these other ones which anti-commute. So A2, A4, A5. So this is, let's just say they are in the group tilde now. So we have A2 anti-commutes with B, A4 anti-commutes with B, and A5 anti-commutes with B. Okay, so now I'm forming sums. So I have the property that A2 plus A4 mod 2, I'll leave that out, commutes with B, just from these relations, and also A4 plus A5 commutes with B. Okay, so I'm not losing all of these rows from the stabilizer generator matrix. I'm only losing one. Yeah? So I'm forming these pairs, and out of, I don't know, M such anti-commuting elements, I'm forming M minus 1 commuting. Okay? So I kept all of the commuting ones. From the non-commuting ones, I lose one. Yeah? So it seems my stabilizer generator matrix has shrunk, but only a little bit. It has lost one column only. And this column we put back in, namely with the observable that's been measured. Yeah? So the post-measurement state is stabilized by the observable that has just been measured. Okay? So the stabilizer after this update is complete again. I go from n rows back to n rows. I haven't lost anything. Okay, so this is the update of the stabilizer matrix, and you see this is all linear algebra, so it is also efficient. And if you want to do all these row manipulations, by the way, this is multiplication with certain matrices from the left, as opposed the Clifford update, which was by multiplication from the right. So let me summarize this lecture. So we have seen two things. So we have seen that the update of stabilizer state under Clifford unitaries and under Pauli measurements is efficient. And that proves the Gottesman-Knill theorem. There's an important theorem in this branch of quantum computation. So that was kind of the phenomenological thing that we did. And also we had a bit of formalism today. So all this stabilizer quantum mechanics maps to mod 2 linear algebra on small matrices. And yeah, and so this is, when you do quantum, should you happen to do quantum error correction sometime, you'll find this formalism all over. Yeah, so that's why it is useful reviewing it. So that was, yeah, this was the Gottesman-Knill theorem, and tomorrow it is quantum error correction. So that's really showing you why the stabilizer formalism is actually quite useful. Good, so that's all for today.